First, I just want to thank everybody for sticking out through late in the workshop. But like Sarah said, my name is Clair Sullivan from the University of Illinois. I would love to have one of my students, actually the one who did this work, up here giving the talk, but very fortunately, he just accepted a postdoc offer. He defended his dissertation a couple weeks ago, accepted a postdoc at Los Alamos, and I think he has to do something like find a house or something like that. So he can't be here today. But talking about isotope identification algorithms and the role that they play in disarmament verification. And really, Arig did a great introduction of why we need information barriers when we talk treaty verification. A lot of times, parties to particular treaties, they don't want to give access to parts or all of the information that could be used to back out their weapons design, and so there is a need for algorithms that can look at parts of the spectrum while blocking out other parts of the spectrum. And so our idea here was that by having better automated isotope identification algorithms, you could potentially offer a more reliable way to limit access to the gamma ray spectrum, specifically when you're talking about non-relevant nuclides. So a lot of treaties, they'll talk about relevant nuclides, non-relevant nuclides. Sometimes they'll even go so far as to specify you must do this measurement with sodium iodide. Sodium iodide is really the focus of our work, low resolution gamma ray spectroscopy. And at the end, what they really want is a red light, green light. This is the thing that's supposed to be here. This is not the thing that's not supposed to be here. But any more information beyond that binary yes or no is information that could potentially be used to back out the design or other sensitive information. Back when I was doing isotope ID evaluations at Los Alamos, and these are old results, this is 2004, what we were observing was particularly off of sodium iodide-based handheld isotope identifiers, the automated identification accuracy was very poor. And what we were seeing was that these identifiers would maybe get the right answer maybe 35% of the time. They were all based off of sodium iodide. Some of the detectors used in the evaluations are the very ones that the IAEA goes out and does inspections with. So the question is, can we somehow improve the automated isotope identification capabilities of these handheld radioisotope identifiers? Okay, so this is sharing my philosophy on isotope identification, and this differs from many other people, such as Dean Mitchell, who's kind of the godfather of the field. But having done the spectroscopy mission for the emergency response community, the way that I approached analyzing a spectrum is I first look at the peaks. And in looking at the peaks, that's giving me my unique fingerprint to the isotope that's present. So I have to determine the centroids of those peaks very accurately, and I want to know something about their areas, because those areas are going to make some sort of sense to me when I start looking at branching ratios and efficiencies of detectors and whatnot. So I want to know the areas, and I also need to know the uncertainty in those areas. After that, I'm going to take all of that information and I'm going to go to some library. Maybe it's in my head, maybe it's in a computer, but I'm going to go and I'm going to say, okay, what isotopes might match this signature? And then I come up with some way of saying, yes, this one is here, no, this one is not here. So this is just kind of a really basic flowchart for how isotope ID works, at least in our approach. And I'm going to talk about how we do each of these things within our research group. First, we start with wavelet analysis. Now, we've heard a lot about wavelet analysis. Many groups do wavelet analysis for finding peaks, but I'm going to try and emphasize how our approach is different from theirs. This is just math. I'm sorry to throw math at you right after lunch. Bear with me, please. I promise it won't last long. But here's the wavelet transform. And as Arig said in the introduction, the wavelet transform, it's just a normal, like a Fourier transform, except in the Fourier case, you're using an infinite signal that you're convolving with your actual signal, versus in the wavelet transform, we're using a finite signal. And it's finite in space and it's finite in frequency. Okay, so I have the wavelet transform, which is applied to my signal here. So wavelet transform is W, X is my signal. And then I get out this matrix that's S here, and that we call the scaleogram, which is what you see in this pretty rainbow picture here. So I have a cobalt-60 spectrum here, and I took the wavelet transform of it. And of course, I can represent this as an integral, but I'm going to do all my math here as matrices in a second. So I get this lovely scaleogram here, which is basically saying if I have a mother wavelet, which is this psi variable here, and I'm going to convolve it with my signal, and I'm going to look for where the two line up. Where do they match, both in frequency and in position? So degrees of strong matching are shown in kind of the yellow shades here, and lesser matching is shown in the blue shades. And then I'm going to look for the extrema in that image, in that matrix. And those extrema are called the wavelet transform modulus maxima lines. So we're specifically, in our case, looking for the maxima because those correspond to peaks. And those are the black lines that you see chained together. And true peaks will have maxima in the scaleogram that cross many, many different frequencies, or scales, the wavelet pseudo-equivalent of frequency. So I can follow these black lines through my scaleogram and know something about my peaks. But here's what's really interesting, is that what we do is we forget everything else about the spectrum at this point. All of the analysis from this point is going to be done in the wavelet domain. And let me tell you the advantage in doing so. I don't know if anybody can see this pointer. Obviously, I have two peaks here. I have a Compton edge here. I've got a Compton continuum here. By doing the wavelet analysis and by analyzing the peaks in the wavelet domain, I can pick the frequencies that are not associated with the Compton continuum. Compton continuum would be a low frequency signal, which would be down in here in my wavelet transform. Electronics noise, on the other hand, would be a high frequency signal, and that would be in this upper portion of my scaleogram. So if I just do not do my analyses in those portions of the scaleogram, then what I'm left with, the only thing that I'm left with in my transform signal are the peaks. And those are the things that we care about. So we're going to do a non-negative least squares calculation here to try and find those peaks. And what we do is we have some sort of basis function, which we spend a lot of time calculating, but we have this basis function that is known. And here we have our wavelet transform, the scaleogram right here. And our goal is to get this vector k. And what that vector k is, it's just a one column ranging from 1 to the number of channels in my spectrum. Anything that's non-zero after this non-negative least squares calculation, we consider as potentially a peak. Okay, so the catch here is, though, obviously I'm going to have to somehow invert this, but that basis function, of course, nature is not kind to us. It's highly singular. We cannot just invert it. So we have to play some games here where we assume that there's some sort of optimal basis function that is invertible, and then we do a singular value decomposition using the more Penrose pseudo-inverse, and we're able to back out that k value. So here's how we get all of that, but that k value actually contains a lot more information than just that. The k value, whatever channel in k is non-zero tells me I potentially have a peak there. But it turns out that the amplitude is proportional to the area of that peak. So now we're talking about single channel resolution of peak areas. That's all well and good, but I also need to understand what's the uncertainty in my peak area before I can do any identification. And so this was a bit of math that we were stuck on for a really long time, but we were eventually able to back out what the covariance matrix is for this solution, and we can take the diagonal elements here, which that will give us the standard deviation on each of my channel measurements, and we're able to get our peak centroid, peak area, and area uncertainty in that one calculation, which is kind of handy. But the key point here, the thing that makes what we do different than all the other people doing wavelet analysis on gamma ray spectra is that we're doing everything in the wavelet domain. And like I said, this has the benefit of only being sensitive to the peaks if you do it properly. We're not sensitive to the Compton continuum. We're not sensitive to the electronics noise, and we can resolve highly overlapping peaks, as we've shown in several papers. So this is a good thing. So back to my original drawing here. We've found our peaks, and now we need to look at some sort of library to say, okay, what might these peaks be coming from? So I'm showing a spectrum taken with sodium iodide of europium-152, which if you were to actually plot out all of the peaks from europium-152 and their associated branching ratios, you'd get all of these little red lines up here. Well, obviously, I'm not going to see all of those in sodium iodide. I'm only going to see a small fraction of them. Now, we could do something naive like, say, take a branching ratio cut. Say we only care about anything that is above like a line like this. But the problem in doing that is if you do that, you actually wind up eliminating a lot of things you care about. One great example of that is plutonium-239. If you did this approach on plutonium-239, you eliminate the 375 and the 414 keV peaks, which are the two that you really care about. So we've played around with different ways to generate our algorithm, or generate our library, but what we ultimately came up with was letting the wavelets tell us where they think the peaks are, and we then are able to do some convolutions to back down to this subset of peaks here, which we would stand a probability of detecting. Now those will not correspond to a truly physical peak. So for instance, this guy right here, this is 2 peaks right here, but we're never going to see that on sodium iodide, so we know that that's 1 peak. The centroid that you get would not correspond to those 2 centroids. It's going to be some sort of weighted average between the 2. So we come up with custom libraries customized to our algorithm, and that turns out to be a really important thing. Okay, so now we've got peaks, we have centroids, areas, area uncertainties in a library. And now we got to do something with it. So what we use is we use the Bayes theorem, we use naive Bayes, and we look at a way of calculating what is the probability of any given model in our database to the data, D, that we have collected. And this is obviously based on some sort of prior probability distribution. What we're calculating here is the posterior probability. The prior distribution, there's a whole art in picking priors for Bayesian analysis. We right now assume a uniform prior. We don't have to, but that's what we do here. And when we wrap all of this up, we start bringing in a lot of the physics here now too. So we look at, we have all these different fuzzy logic scores here that tell us how many peaks in our library were matched to our data, were the areas of the peaks scaling right, for instance. We know that higher energy peaks are attenuated less than lower energy peaks. So if I add attenuation, those ratios need to change accordingly. So we do all kinds of different fuzzy logic scores. We compute the naive Bayes probability for each model in our library, and we get some good results. So for instance, here is a spectra we took at DAF, a 15-second spectrum of the BeRP ball, 4 centimeters of poly around it, distance of 1.2 meters. We obviously see the characteristic signals of weapons-grade plutonium right here. We've got all of the 640 keV features here. And this is just a sampling of 10 different spectra and the identifications that we got. Now, I have 3 columns here. The first column is of all of the models in our library. And right now, our library is based on the ANSI standard for handheld isotope identifiers, plus several more isotopes that are of use to us. So it's a pretty complete library. And then we come up with up to 3 combinations of each isotope. So every isotope in the library can be combined with every other isotope and then another isotope. Okay, so that's as far out as we go right now. We could add 4 or 5 or however many. But we look at which model in our library had the highest posterior probability. And that's what's shown in this column here is ID. So this is the single model with the highest posterior probability. And we see here that in all 10 cases, we got americium-241 and plutonium-239, which that is correct. The BeRP ball has a significant amount of americium-241 in it, so we absolutely should identify that. And you can see the posterior scores for each of these calculations. And the good news here is that these are all some pretty significant numbers. The next highest posterior score was really small. But we also might just care about, well, is there plutonium present? Is there uranium present? And so that's just this plutonium-239 presence. That's the posterior probability of just plutonium. We can do this also for the Rocky Flats shell. So this is 13.1 kilograms of highly enriched uranium, 15 seconds, distance of 1.2 meters. I'm not trying to pull the wool over anybody's eyes. You can see that there are misidentifications in here, there are false identifications in here. But the bottom line that everybody cares about is, okay, how correct is an identification? And that might sound like a simple question. It's actually a lot harder than that, though, because you have to look at, well, okay, you know, this top one here, I got the uranium and I got the thorium. Do I really care that it got that gallium? Is that a correct identification or no? So we've been, here's shielded HEU. I just have to show this really quick. 60 seconds through a ½ inch of iron, and our model with the highest probability is straight U-235, which is great. Okay. We've been leveraging work that we have going on with DNDO right now through their algorithm improvement project, which is something that Dean Mitchell and a lot of other people have put together, is to come up with a statistical measure of comparing isotope IDs side by side, apples to apples. Okay, and so what they decided to do is calculate this F score, which is just the harmonic of looking at our precision, the probability that a positive ID is actually correct. So I said uranium, and uranium was actually there. And then recall R, that what is the probability that an isotope is actually ID'd? So In doing that, we can calculate precision and recall based on the true positive and the false positive and false negative rates here. And then we calculate this F-score as this first harmonic shown here. So I'm putting this up today. This is the first time we've shown these results, and this is just kind of putting a flag in the ground saying, here's where we're at. Other groups are doing isotope ID work, and I very much would like to encourage the community. We wanted this for at least 15 years, having a way to compare algorithms side by side. So here's our F-scores. Now, you see that there are weighted and unweighted, these WF weighting fractions. This means that we care more about certain isotopes than others. We don't have to use them. But what we see here is that our F-scores are around 67%. Our precision and recall are shown here as well. The bottom line here, though, is that the way this algorithm works, it was generated for high purity germanium. Now, you would not expect sodium iodide to get 100%. But the thing that's useful about this is it gives us a way to say, okay, we made a change in this algorithm. Have we achieved some sort of goodness? Well, I can measure that now in my F-score. And this F-score is calculated out over hundreds of different isotope combinations. It's not just, the two combinations that I showed you here. So this is a good positive step that DNDO is taking in the right direction and can benefit us here in CVT. Okay, future work. We have several companies who have approached us with interest in licensing our algorithms, so we're working with our lawyers on doing that. Through some other funded work, we actually have found a new method of doing this entirely that doesn't use any of this. It goes straight into neural networks. And the cool thing about that, and I'm not going to say anything more than just to give a little hint that we think maybe, possibly, we might be able to do crude isotopics using that approach. But stay tuned on that. I'll say something about that at next CVT. And all this stuff is stuff that I've said before. Just a couple products that we've put out this year. One PhD going to Los Alamos in mere minutes. Some publications this year. I do want to advertise a conference that we have coming up that NNSA has been helping us with prior to all the changes within the office, which is IRMA, the Industrial Radiation and Radioisotope Measurement Application Conference. It's going to be the week of July 9th in Chicago. It's a great place to send your students to give presentations with a peer-reviewed journal article. So please consider coming out, and if you want to volunteer to be on the committee, I'm happy to have you. Last, everybody's asking me, Michigan and Illinois play this weekend. Michigan is my alma mater, Illinois is my employer. Who's going to win? Well, I figured I had to do this as a Bayesian calculation. So, unfortunately, Bayes' rule breaks down if you have a 0% probability of a thing. So if I was only to calculate this based on this year, Michigan's probability of loss right now is 0%. So Bayes breaks down for Michigan this year. So I have to use historic data. I'm going through the entire history of both universities' football programs, where I have the probability of Michigan's winning and Illinois' winning and past records and whatnot, and I can calculate this all out, and you've heard it here first. By the way, this is how Nate Silver does his calculations, but you heard it here first. Go blue. Thank you.
I was at a talk he gave probably 2 weeks ago. I think Robbie was there too. He literally said we are going to hire 180 people in the next fiscal year, and that started a couple weeks ago. So if you look at it, lab